Hello again, everyone. Welcome to our briefing on the ELaNa CubeSats, also flying as auxiliary payloads on the Delta II on Thursday morning. We will also take questions from the media at the conclusion of the presentations, and then social media can also ask questions as well by using hashtag AskNASA. And we'll start first with Scott Higginbotham, who is the NASA ELaNa Mission Manager from the Kennedy Space Center in Florida. Dave Klumpar, the Firebird 2 Principal Investigator, and who is the Director of the Space Science and Engineering Laboratory at Montana State University in Bozeman, Montana. Then to John Bellardo, the ExoCube Co-Principal Investigator from the California Polytechnic State University in San Luis Obispo. And finally to David Ryder, the Griffiths Principal Investigator from the Jet Propulsion Laboratory in Pasadena. So we'll start first with Scott Higginbotham, the ELaNa X mission, ELaNa 10 mission manager. Scott?
Thank you, George. For those that may not be familiar with what a CubeSat is, basically it is a research nanosatellite that conforms to certain standard features, in particular relative to size and shape and volume. The smallest CubeSat that we fly is what we call 1 unit or 1U. And a U is 10 centimeters on a side, so a 10 centimeter cube. On this particular mission, we have 4 satellites that we're launching. 2 of them are what we call 3U, meaning that they are 30 by 10 by 10, roughly. And the other 2 are 1.5U, which means that they are about 15 centimeters by 10 by 10. These 4 CubeSats will be launched into space, contained within some standard dispensers that we've procured. The particular dispenser we're using on this mission is a P-Pod, which is a poly-picosatellite orbital deployer. The P-Pod is designed and built by the fine folks up at the California Polytechnic State University in San Luis Obispo, or Cal Poly, and this is a P-Pod right here. The P-Pod is essentially a very sophisticated jack-in-the-box, but you'll see there's no handle that you can crank. It is a metal box that contains the CubeSat to keep the CubeSat from harming anything and to keep it contained on ascent. At the appropriate time on orbit, the signal is sent from the launch vehicle to the P-Pod. There is a non-explosive actuator that goes right here, and that actuator then allows the door to open. The door opens up, it's spring-loaded, and then as you can see inside, there's a pusher plate that's attached to a large spring. That large spring provides the impulse to push the CubeSat out, or CubeSats out, into the space environment at over 1 meter per second. So, the 4 CubeSats that we're flying on this mission were all selected for flight through the NASA CubeSat Launch Initiative, or CSLI. CSLI provides opportunities for educational and nonprofit organizations and NASA centers to get CubeSats launched into space, either flying along as auxiliary payloads on unmanned vehicles or being flown up and ejected from the International Space Station. The CubeSat Launch Initiative selection process is competitive, and each proposer has to come forward and demonstrate the merit and feasibility of their satellite that they're proposing. And also they have to demonstrate how that satellite meets one of NASA's strategic, or more than one of NASA's strategic objectives relative to technology demonstration, science and exploration, or education. And in the case of the CubeSats you're going to be hearing about here shortly, several of them meet objectives in different areas. Since 2010, we have selected 114 CubeSats for flight through CSLI, of which 33 have been successfully placed into orbit to date. And come Thursday, there will be 4 more to add to that list. ELaNa missions, or Educational Launch of Nanosatellite missions, are how we go about implementing the ultimate goal of CSLI, and that is putting the hardware into space. What we do at the Launch Services Program is we look for rides going into orbit that are going at the right time, in the right direction, and at the right price. And if we can find a match there, then what we will do is build a manifest to fly on that mission. We'll then procure the launch service, procure the dispenser and the integration services that go along with that, and then we'll ultimately go evaluate all that hardware to make sure that it's suitable for flight. Our prime directive is that we can do no harm. And so we have to spend a tremendous amount of time and energy proving that the CubeSats and dispensers represent no risk to the baseline risk of the mission overall. We can't harm the launch vehicle, we can't harm the primary satellite, we cannot harm the public. And for this mission, ELaNa 10, again, we have 4 CubeSats that are flying up in 3 different P-pods. The P-pods are mounted on the second stage, on the V-struts of the second stage, and are pointed down and away. And there are signals that will be sent at the appropriate time in orbit for the doors to open and the P-pods to be ejected. Specifically, our separation timeline is set up such that the first CubeSat, actually first 2 CubeSats, the Firebird CubeSats, will be ejected 1 hour and 45 minutes and 7 seconds after launch. The next P-pod will then be commanded to deploy 100 seconds later, and that'll be Griffix, and then 100 seconds after that, ExoCube will be deployed. Once the CubeSats are deployed, they're on their own, and they're the responsibility of the sponsoring organization to control. It's not NASA, it's the institutions that you'll be hearing from next. The satellites will not start sending radio signals to the ground till about an hour at the earliest after they're deployed. And so the earliest that we expect that we will start hearing from the CubeSats is later on in the afternoon on Thursday or into Thursday evening. So in summary, all of our hardware is on board and it's ready to go fly. It's a thrill to be here. And I do want to acknowledge 2 groups before I pass it over to Dave. The first is the fine team again at Cal Poly that built the CubeSats, or built the P-pods rather, and did all of our integration work for us. That team, Alicia Johnstone, Ryan Nugent, and Justin Foley did an absolutely outstanding job. And then lastly, I want to acknowledge our mission integration team back within the Launch Services Program led by Bill Atkinson, who's here in the room with us. They are responsible for doing all of the work to verify that all of this hardware meets all of the stringent standards that NASA makes us apply to this hardware, and they did also an outstanding job. So with that, George, back to you.
All right. Thank you, Scott. And now to Dave Klumpar, the Firebird 2 Principal Investigator from Montana State. Dave?
Thank you, George. I'm very pleased to be here to represent the Montana State University, University of New Hampshire combined Firebird 2 team on the occasion of our upcoming launch as an auxiliary payload with the SMAP mission. I want to thank NASA's Earth Science Division for allowing our little guys to fly with their big Earth Science mission. Also want to thank the NASA Launch Services Program ELaNa team for providing these opportunities that allow the students who've designed and built these satellites to actually see the fruits of their labor pay off by operating the spacecraft in the space environment. You know, it's one thing to do PowerPoint presentations and studies in an undergraduate environment, and it's something else to actually get out there, put that learning, that knowledge that you've gotten from the classroom to work, and actually build a piece of hardware and get it to its destination and operate it from the space environment. That's just huge for the students, and we wouldn't be able to do this without the support of the Launch Services Program ELaNa team at Kennedy Space Center. So thanks again, Scott, and please pass my thanks on to Big Daddy back there at Cape Canaveral in the Launch Services Program. I think I'm referred to the gentleman who actually heads up and really makes the ELaNa program what it is. So if I can have the first graphic, I want to talk a little bit about the scientific mission of Firebird. It is a scientific investigation, as I said, primarily built by students at Montana State University and at the University of New Hampshire. Montana State really provided the spacecraft bus and did the integration and testing work, while the scientific payload was designed and built at the University of New Hampshire. The investigation is supported by the National Science Foundation, and as you've heard today, is being launched by NASA. So we have a lot of government presence in our process. Let's get to the scientific purpose. The purpose is to investigate a mysterious phenomenon known as, a little bit of a technical term here, relativistic electron microbursts. I'll tell you a little more about that, just briefly. But why do we do this? It's important because the Earth's Van Allen radiation belts, which is the reservoir of the very intense radiation that can damage spacecraft and cause health problems with human beings, that reservoir is a fairly stable environment some of the time. But there's a mysterious process going on out there that jiggles the Earth's magnetic system in such a way that some of those very energetic, they're called killer electrons for obvious reasons, can be dumped into the Earth's upper atmosphere and precipitate out of the radiation belts, causing perhaps one of the most significant losses from the Van Allen radiation belts. We don't understand this process. The extent of the process hasn't been quantified. And so the Firebird mission, if I could have that view graph back, the Firebird mission is focused on understanding, and the words of the acronym really tell it. We're looking at the relativistic electron burst intensity. How intense are these radiations as they rain down on the Earth? What is the range? What is the spatial extent over which they bombard the Earth? And how dynamic are they? In order to do this, we fly the 2 Firebird satellites in a dog chasing a cat formation, deep, well above the Earth's atmosphere, but very low altitude compared to where the Van Allen probes are measuring the radiation out there in the space environment. Those Van Allen probes, built by NASA and launched about 2.5 years ago, are embedded in this radiation belt environment, and they're understanding exactly, they're measuring all of the phenomenon that are of any importance that's going on out there. Unfortunately, they're blind to the very important, very small spatial dynamic region. They're blind to what's being dumped into the Earth's upper atmosphere. And so with these 2 focused Firebird satellites, we look down at the upper atmosphere and see what's actually coming in, and the Van Allen probes are able to tell us, here's what we saw out there at the same time you saw these things dumping into the atmosphere. So let's go on to the next slide. It shows photograph. So in order to accomplish this investigation, it takes the 2 satellites, as I described, cat and dog. And each of these satellites have been built by students at the at Montana State University, and the payloads built by students at the University of New Hampshire. They're identical, but they're very diminutive, as Scott just described. They're about 10 centimeters on a side, about 15 centimeters tall. Nevertheless, they carry all of the fundamental hardware that the much larger brethren like SMAP carry. They have, as you can see in the image, they have solar panels to charge the batteries that are providing power to the satellites during eclipse, through a power system that very carefully controls and monitors the power being distributed around the satellite. They carry full downlink communications. There are RF transmitter on board, antennas that are wrapped around the sidewalls of the spacecraft and deployed once we get into orbit. There's a receiver on board to receive and decode uplink signals, and finally a GPS system to tell us where we are and to time the relative timing between the 2 satellites. And of course, last but not least is the very important scientific payload. So I want to close with a little video. The School of Film and Photography at Montana State University produced this little 30-second video regarding the program and the missions that we're accomplishing with these CubeSats. Can we roll that video?
At Montana State University, we build real satellites for NASA. To most people, the MSU campus looks like this, but to me, it now looks like this. Our satellite has orbited the Earth over 5,000 times, advancing technology throughout the world. We work together, we shape the future.
The university is so proud to be a part of this program, augmenting our students' formal education with such experiential activities, that this video was shown during the halftime break at the Brawl of the Wild, as it's called. That's the traditional once-a-year annual battle on the football field between Montana State University and the University of Montana. It was shown on national TV during that game. Don't ask me how the game came out because I don't really follow football. And I think I'll turn it back to you, George.
All right, thanks, Dave. And now to John Bellardo, the ExoCube co-principal investigator for California Polytechnic State University in San Luis Obispo. John?
Thank you, George. I'm pleased to be here representing the ExoCube team. Despite the fact that all these satellites are small, there's a huge team of folks that goes behind them to help make them what they are. So I want to start out by thanking a number of the institutions that have been involved with ExoCube to make it as successful as it has been thus far. First and foremost, Scientific Solutions was providing a lot of the leadership on the project, right, in both technical and scientific. We've also been working with the University of Wisconsin-Madison, the University of Illinois Urbana-Champaign. On the science side, they have a number of scientists who have contributed to the science design of the experiment and are standing by to begin analyzing the data as soon as the data starts coming down, approximately a month or so after we're deployed from the Peapod. We also worked with NASA Goddard. They were involved with making the science instrument that we have in the CubeSat itself. And then finally, the team at Cal Poly was involved with designing the bus, building the satellite, and integrating the instrument from Goddard and doing all the final testing. The Cal Poly team is the team that I am partially responsible for advising. They're a team of students, and as is the theme with these satellites, they're largely student-built. They provide a phenomenal educational opportunity to get real life experience for the students to complement their classroom education. It's a wonderful opportunity, and a lot of thanks goes to the ELaNa program to help facilitate that. So, thank you.
Thank you, John. And next to David Ryder, the Griffix principal investigator from the Jet Propulsion Laboratory in Pasadena, California. David?
Yes, good afternoon. I'm going to tell you about Griffix. Griffix stands for GeoCape ROIC In-Flight Validation Experiment. So in some sense, this is a little bit different than the other two in that we are a technology validation flight. And I want to tell you a little bit about why we're worrying about validating technology, and it's actually in the title of it's in the acronym of our experiment, but it's GeoCape. GeoCape is a mission that's been envisioned by NASA for quite a while, and a lot of people have been working on it. But when we first started thinking about GeoCape, we realized fairly early on that there were some key components that we needed to develop in order to pull off the mission. Now, what makes GeoCape unique, at least in our thinking, is that it will be located in a geostationary satellite, which means that it's stationary with respect to the surface of the Earth. The idea being then that you can look over a big area of the Earth many, many times a day, as opposed to low Earth orbiting missions such as SMAP, where you can only see some places 2 or 3 times a week maybe. The problem is that we didn't have detectors that would take data fast enough to be able to allow us to do continental coverage over periods of several hours, which is what our objective was. And most importantly, to be able to measure the composition of the atmosphere over those time and spatial scales. So we needed to develop a detector that allows us to do that. And that's what we are going to test on this Griffix flight is the readout integrated circuit, which is what ROIC stands for. I have one here as an example. It's a fairly tiny little piece of hardware, but it's got a whole lot of parts in it. This is essentially a detector array that's got 128 by 128 pixels. You multiply that out, that's about 16,000 detectors. But even better than that, in order to be able to make it go as fast as we needed it to go, we end up building analog to digital converters into every pixel. So essentially, this is an all-digital focal plane detector array, which is truly unique in the fact that it can digitize at very high rates. This one runs at about 8 kilohertz, which is really unprecedented. Well, every time you go and make something like this, you always worry that you forgot something and it won't work right when you get it on orbit. So a CubeSat is really a rather ideal and efficient and quick way to go about demonstrating that you can actually make the same thing work in space, and that's what we've done. This is our Griffix model, a plastic model of our Griffix spacecraft. It's a 3U. We built a camera that is down here in the bottom half of this. The outside is covered all with solar panels that provides the power for the satellite. The rest of it is just I want to be careful. I was going to say standard electronics. Nothing standard in here. The data handling system, the command and data system, the radios, the power subsystem. And so combined, we're going to be able to go and put our camera in orbit and take pictures of the Earth and demonstrate that our readout integrated circuit and the works the way that we need it to work to be able to go do the GeoCape mission. I also want to make sure that I acknowledge the Earth Science Technology Office at NASA headquarters. They've been very good about funding the development of technology for future missions for Earth sciences. And in this case, they've been very generous with us. Along with that, the educational part of it, we also are partnered with a university, which is the University of Michigan. This Jamie Cutler's group, who put several 3U CubeSats into orbit, and we depended on their experience. And they've also had a great time with all their students trying to figure out how to make all this stuff work. So at that, I'll close and turn it back to George. So.
All right. Thanks, Dave. We're going to go back now to John Bellardo from Cal Poly, who will discuss some about the science objectives on his mission. John?
Thank you, George. The science objectives, the science behind ExoCube is to measure the density of particles in the upper atmosphere, specifically particles that have an atomic mass of less than 40. Measuring the particles in place in the upper atmosphere is very important. It's something that has not been done in approximately 30 years. We've been largely relying on ground-based measurements, which have inaccuracies and require calibration in the instruments to be able to take reasonably accurate readings through the atmosphere. So we're excited to provide the opportunity to take measurements in place in the upper atmosphere, use them to recalibrate or refine the calibration of existing ground-based instruments, use them to refine and validate models that predict what these densities should be over time, so that long after ExoCube is no longer functioning or no longer in orbit, we can still enjoy some of the benefits of the science data that's taken. This is the engineering model for ExoCube. It's a 3U satellite. Looks like most of the other 3Us when it's deployed from the P-pod. One of the unique features that ExoCube has is it has deployable booms. So a little while after deployment, there will be booms on either side of the satellite, this is just one, that deploy, that help stabilize the satellite so that it's always pointing in the correct direction so the particles enter the mass spectrometer correctly. So that's one of the interesting features that the students at Cal Poly helped build into the satellite. Thank you, George. Back to you.
All right. Thanks, John. And we're ready now to take questions. And remember, social media can also ask questions by using hashtag AskNASA. And we'll go first to questions here in the room and then take social media. Justin.
My question, two parts for Scott. I was wondering if you could tell us what orbit the satellites will be dropped off at. I think Vern had mentioned that there's going to be a burn after SMAP separation. And also, for all of you, how long do you expect your respective missions to last?
All right, we'll start, and I'm embarrassed. I don't have that committed to memory. I do have it in my computer, so we'll get back with you on that. We are separating, I think it's like a half a degree of inclination from the SMAP orbit, just so that we get enough away that we don't have any conjunctions, but we'll get you the details on the orbit.
I could comment. I'll help Scott answer the question. My memory serves me right, and I'm not sure it does at my young age anymore. But I believe that the initial parameters in terms of altitude and apogee is at about 600 kilometers, and perigee is down at about 450, if I remember that right. So it's a little bit elliptical, and the parameters predict that we'll be in a truly sun-synchronous orbit. Now, these are pre-launch predictions, so that we pass over, the satellites pass over each of our ground stations at exactly the same time, twice a day, every day at exactly the same time. There's no phasing, they're sun-synchronous. And so we're very excited to be in that kind of an orbit. Lifetime, that orbit will give us a very long lifetime, close to a decade or more for the satellites to actually be in space before they decay into the atmosphere, and they will decay into the atmosphere. They don't create space debris. We clean them out naturally. And operationally, we would be disappointed if we don't get at least a year of operation out of the 2 Firebird satellites. We've designed them to operate for that period of time. There are no consumables. There's no reason why they shouldn't last, knock on wood.
Comments from the others? John?
For ExoCube, the hoped lifetime for the operational side is 6 to 12 months. But again, there's nothing, if we could last a lot more than 12 months, we continue to take measurements and continue to get data, and that would be wonderful.
Yes, and my answer is pretty much the same. What gets in the way with them coming down is just drag, space drag, and eventually they'll fall out of the sky. And so they'll go for almost a decade, and there's nothing in, at least in Griffiths, and I think it's true of the others, that would cause it to quit working in something any other than years. So we take a few, they are CubeSats, they're built by students. We do take a few shortcuts. And the good thing about that is we get to try out an awful lot of electronic hardware that we probably wouldn't be allowed to do on a more expensive mission. And so part of this, in this case at least, we're kind of anxious to find out how all the other electronics work too. So it's all a big experiment.
Other questions? Here, Janine.
How valuable are these, this kind of hands-on lesson for the students?
I'll answer that because I work at a place where we actually hire a lot of these people that graduate, and it makes a tremendous difference. They come in with experience being around spacecraft. They understand a little bit about the space environment. They understand a little bit about what you have to go through to get things launched. They understand a lot about what you need to do to test things so that they will work with some reliability when you do launch them. So it's extremely valuable.
I'll just add a comment on the fact that the students they're practicing their careers. They're practicing what they've learned in the classroom, but they're practicing it in a very interdisciplinary way. When the students come together to design and build one of these satellites and take it through test and space qualification, we have mechanical engineering students, thermal engineers, computer science students, computer engineering, electrical engineering, and physics students all in the same room together, and they're all bouncing their own little ideas off of each other. Well, we should do it this way. And the other guy says, no, I can't support that much power on my thermal system. And so it's a real interdisciplinary interaction that hones their skills and makes them so valuable to JPL and the other employers in the aerospace industry.
All right, we can take social media questions now. We got some that have come in.
All right, wonderful. This first question comes from Twitter user Harm, who asks, what are the advantages of CubeSats over normal satellites, and how will these satellites benefit NASA?
Let me take the second one first, and how they benefit NASA is, one, we have a mission to help improve the educational opportunities for students in the United States relative to science, technology, engineering, and mathematics. And as you heard, this is an absolutely outstanding way for students to get real-world experience on building flight hardware that they can take into their careers and hopefully keep them motivated to stay in the aerospace or other technical fields. So then on top of that, we get the opportunity to go demonstrate technology, as Griffix is going to do. And as all three satellites are going to do, we gain scientific knowledge, which is also one of NASA's strategic objectives. So, we get all the above. And as far as benefits over larger satellites, well, I think you heard that too. You can experiment. The cost is such that we can try and fail and try again and fail, or learn something every time incrementally and get better at something without making the huge investment that one would have to make if you were to buy a large satellite and invest in the launch service for that large satellite.
I'll just add a word, if I could, about the technology development that can be done with these very small satellites. I happen to bring along today the next satellite that it's a copy of the structure of the next satellite that Montana State will be building, and this is a completely 3D printed flight satellite. It's not a model. It's not just a test demonstration. This 3D printed structure will actually fly in the space environment. It's not made of aluminum, it's all plastic. And that's the kind of technology that we can test in the space environment at a very low cost with CubeSats.
And I'll add one thing, inexpensive and faster. I mean, Griffix, which I think, well, we took a little longer than we anticipated, was less than 3 years from when we first thought about it to when we're actually going to launch it. That's absolutely remarkable in the space business. So.
Next question comes from Facebook user Warren, who asks, were the students at Montana State completely autonomous, or were they asked to follow a specific template due to the size and safety restrictions, or were they consulting with NASA engineers frequently, and if so, how frequently?
There is a very specific requirement on the size and mass of these CubeSats. You'll see that they all have very identical features from the outward appearances. Internally, everything that goes into them is entirely up to the design team for each specific mission. Our students are advised by a couple of full-time spaceflight engineers that work with the faculty, myself and another faculty member, to guide the students, but they're left a lot on their own. A big part of this whole adventure is trial by error and trial by fire. In other words, we throw it at the students to come to the table with a job well done, and we help them along the way. We mentor them, we guide them, we run regular meetings each week with the students, but the ultimate design work and the fabrication is done by the students themselves.
And to add on to that, from a government perspective, we levy a fairly lengthy list of requirements on each satellite provider to ensure that the hardware they're providing is going to be safe to fly. And so we work then with our integration contractor, Cal Poly, and with each of the teams to make sure that they have provided all the evidence necessary to prove to independent authorities that this hardware is safe to go fly. That interaction takes place over the course of the campaign, a little over a year in total, and in the end we have all of the evidence necessary to show that we are clear to fly.
Excellent. You just actually answered Twitter user Joe's question about the basic required functions for CubeSats, so thanks for taking care of that. Moving on, this question comes from Twitter user Scott, who asks, what is the average total cost of a CubeSat, including development, launch, and mission operations for 1, 2, and 3 CubeSats?
Well, let's see. I think from what I've heard from, because there's multiple pieces of that, and I don't think, none of us control all the pieces, but we go out and buy the integration services, the dispensers, the launch service, Meanwhile, the satellite providers pay for building and testing the satellite, and then we all pay for the paperwork that goes along with trying to prove that it's okay to fly. I think it's probably safe to say that on average it's close to $1 million or $2 million in the end in total for everything. But I think it varies widely depending upon the sophistication of the scientific instrument that's flying on that satellite. Every CubeSat that we deal with is different. Some have very sophisticated, very expensive items inside, and some are very simple and straightforward. So there's a wide range, but probably if I were to say on average, it's $1 to $2 million.
Additional questions on social media?
Indeed, we have a few more here. This one comes from Twitter user Larry, who asks, do CubeSats have active control systems?
They're working on it. In fact, some do. Mine does not. It's all passive. It sort of flies. It's got magnets in it and it flies on the magnetic field lines of the Earth. But I know at JPL we're working on several where we actually have gas propulsion system. That's particularly important if you start thinking about sending a CubeSat out of Earth's orbit, because it takes some energy to get it on its way to where it's going. So Griffiths doesn't. I don't.
Griffiths doesn't. ExoCube does have attitude control, determination control, absolutely. And as you said, it depends on the satellite, depends on the mission, whether or not you need it. Obviously, that's going to increase the complexity and drive some of the costs of the satellite if you need to include attitude control. ExoCube does not have full 3-axis attitude control. There are definitely satellites you see that have the full 3 reaction wheels and can have full 3-axis control. ExoCube, as I showed you the booms before, that's part of the system, right? They have the gravity gradient booms, one on either side, and then there's a single wheel in the center which helps stabilize the axis in the other and stabilize the satellite in the other axis. So it uses gravity gradient to help stabilize 2 of the axes, and then it uses the wheel to help with the third. So it's a form of attitude control. It's not as precise as a 3-wheel system, but that wasn't necessary for this particular mission.
Well, a follow-up question to that comes from Twitter user Nil, who asks, how does the boom ensure that a CubeSat will face towards Earth rather than rotate freely in space?
The gravity gradient effect works by gravity pulling slightly harder on the bottom boom versus the top boom, and that tends to cause the satellite to stay oriented with one of the booms facing Earth. There are a couple of other coils here that we have to align the satellite roughly in that orientation before we deploy the booms, so we can ensure that the satellite is correctly oriented vertically before we try to stabilize it in the 3rd axis.
All right. This next question comes from Twitter user Matthew, who asks, could something like this be used for conducting similar missions that go along with things to the moon, asteroids, or even Mars?
Oh, yeah. Absolutely. Yeah. And in fact, we're going to go do that. We have some missions that we're working on right now to send some CubeSats along with larger spacecraft to Mars. And then I'm actually working on a mission, the first SLS mission that's coming up, EM1. We're going to fly CubeSats on that mission that are going to go to the moon, to near-Earth asteroids, and out into deeper space to do other interesting things. So absolutely, NASA is interested in seeing that happen, and we're going to make it happen.
I just add right now there's an opportunity to the scientific and university community broadly from NASA's Planetary Sciences Division, and right now as we speak there are dozens of teams out there working on their proposals that are due on March 13th to fly on this EM1 mission or a similar mission to do planetary science. Very much so.
It's a great seg to this question here from Twitter user Elaine, who asks, how do you choose which universities to partner with for projects like these?
There's long established sort of collegial relationships, I would say. We typically know who's good at one particular subsystem or one particular area. Typically, as was described earlier, we do compete for funding for all these missions, so we want to put the best team forward that we can. We get together, we choose a particular science investigation, and that drives the instrumentation and the hardware that will be developed. So the teaming, you know, it's a lot about who you know, kind of, but it's not it's Forming the team is not a very formal process. It happens at meetings, it happens through email, and eventually a team comes together and things start to click. But we pretty much know each other before we start.
All right, we'll take one more social media question before we wrap up.
Last question comes from Twitter user Amber, who asks, what type of data and what format do these CubeSats collect, and how is it received on Earth?
I'll start that one. The data and the format that the data is very specific to the mission, right? So the data format that we get out of the mass spectrometer on ExoCube is going to look different than the data format on other missions. Now, in terms of downlinking it to Earth, we do use a largely standardized format for communicating the data over the radio, namely using AX25, which is part of the amateur radio community. And we do this for interoperability so that the ground station that we have at Cal Poly can participate in tracking Griffix and helping get the data from Griffix, tracking Firebird, helping get the data from Firebird. So as a community, we try to work together to downlink the data, and that level of interoperability does exist. When the satellites, when it comes to the actual science data and the format of the data itself, that varies largely from mission to mission.
I'll just underscore that the radio system on which that many of these CubeSats are transmitting from is readily heard by and translated by amateur radio folks. And there's a community of amateur radio enthusiasts around the world, and a subset of that community is very active in tracking satellites as they're launched. So we expect a colleague from Germany to be the very first person to hear our CubeSat. If the orbit predict is right, we'll turn on just as we cross the Mediterranean heading north, and Germany will be right within the data band through which the satellite can be heard. So these amateur radio guys, AMSAT community, really is really helpful for this entire university community, and we're really pleased that those guys and gals are out there helping us out.
All right, any further questions here in the room? All right, in that event, that's going to conclude this briefing and a programming note about our launch coverage on NASA television, which will start at 4 a.m. Pacific time, 7 a.m. Eastern on Thursday morning. Thank you very much.